If you've ever had a dental X-ray, you know the drill. The technician drapes a heavy, stiff apron over your chest before stepping out. That apron is lined with lead. But why lead specifically? Radiation is essentially invisible energy on the move. To stop it from passing through your body, you have to force it into crashing against solid matter, dissipating that energy before it reaches your cells. But stopping it isn't as simple as dropping a heavy block in the way. Radiation comes in distinct forms: electromagnetic rays, neutral particles, and charged particles. Each type interacts with matter in entirely different ways, depending on its specific energy level and electrical charge. You cannot rely on a universal slab of steel to protect you from all sources. A shield must be precisely engineered for the specific subatomic car crash it is trying to intercept. Effective shielding requires matching the exact physics of the incoming threat to the atomic structure of the barrier. Let's start with electromagnetic radiation, like X-rays and gamma rays. When these photons try to pass through a material, their primary obstacle is the material's electron cloud. If the incoming photon has relatively low energy, we get the photoelectric effect. The photon hits an outer electron, transfers all of its energy to it, and ceases to exist. The target electron absorbs that hit and is violently ejected from its orbit. This is exactly why the dental apron works so well. A single lead atom has 82 electrons. That incredibly dense electron cloud is perfectly suited to absorb low-energy X-ray photons through these exact photoelectric collisions. This diagram illustrates what happens when the energy increases. Known as the Compton effect, a mid-energy photon acts more like a ricochet. It transfers a fraction of its energy to the recoiling electron at angle phi, while the weakened photon scatters at angle theta. Push the energy even higher, past 1.02 mega-electron volts, and the photon goes through pair formation. The pure energy of the gamma ray converts into actual physical mass, spontaneously generating a negatron and a positron. Across all these scenarios, survival against electromagnetic threats comes down to the density of the target's electrons. Every collision, whether a total absorption or a ricochet, bleeds off the incoming photon's energy until it is entirely spent. How do scientists use this subatomic theory to build real-world protective barriers? They calculate the precise thickness required to safely dilute the beam. Every material is assigned a specific mathematical rating for its stopping power, known as its mass attenuation coefficient. This slide shows how engineers plug that coefficient, the Greek letter mu, into the Beer-Lambert equation. By factoring in surface density and applying a polynomial correction, they compute exactly how thick a barrier must be to drop radiation intensity to a harmless level. This mathematics translates subatomic chaos into predictable, life-saving blueprints for engineers. There is a blind spot in this strategy. Neutral particles, like neutrons, have zero electrical charge. They completely ignore the electron cloud and will pass right through a thick lead wall as if it isn't there. Without an electrical charge to repel them, fast neutrons cruise straight past the orbitals and slam directly into the atom's central nucleus. To stop a fast neutron, you have to drain its energy through a series of elastic collisions, a process called moderation. In subatomic billiards, a projectile loses the most speed when it hits a target very close to its own mass. This equation calculates the maximum fraction of energy a neutron can transfer in a collision, where A is the target's atomic mass. The fraction transfers reaches its absolute maximum when the atomic mass is 1, which is hydrogen. This specific calculation is why engineers abandon heavy lead when dealing with neutrons. Instead, they submerge the cores of nuclear reactors in massive pools of hydrogen-rich water to systematically shield and slow down the lethal particles. Whether it's X-rays violently ejecting electrons or neutrons bouncing off hydrogen nuclei, every invisible radiation threat ultimately boils down to a predictable transfer of energy. Mastering these specific collisions moves us past the need for passive barriers. We can now manipulate the radioactive environment itself. We utilize these reactions to capture data. By predicting the secondary X-rays released when a shell is vacated, or the specific angle a neutron scatters, we can detect those signals to map the interior of the human body. Decoding these kinematic rules turns an invisible threat into a predictable variable, allowing us to navigate and utilize the atomic scale with clinical precision.